Hola, bienvenidos a todos a otra sesión del coloquio del Instituto de Matemáticas. Hoy tenemos el placer de tener con nosotros a Subrata Majumdar, que está haciendo una estancia postdoctoral aquí en nuestro instituto. Y nos su título es Boundary Feedback Stabilization of Heat Equation and Beyond. Muchas gracias, Subrata, por aceptar la invitación y adelante.
Thank you for the invitation and for the introduction. So today I am going to present the boundary feedback stabilization for heat equation with a method which is called backstepping method. So first we start with the notion of stability and stabilization. We will see some example for simple ODE, and then we will discuss the main topic of this talk, which is backstepping method for heat equation. But before to the heat equation, I will discuss this method for a simple ODE. So then after the heat equation, we will explain some feedback stabilization result for linearized compressible Navier-Stokes equation, and then a nonlinear model Fiduk-Nagumo system. Okay. So in general, the main question in control theory is framed as, so let's say we have a dynamical system. We try to find a control Q such that if we put this control Q in the system, then our system behaves suitably as we desired, right? So for formulate a control problem, we first need two spaces. So here we consider two Hilbert space, H and Q, and this is the dynamical system. It can be ODE, it can be PD according to the context. So U dot T equal to A of UT plus B of QT. Okay. So here U is the state, which is a H-valued function. That means at time T, UT belongs to this state space H. Okay. So U naught is the initial state, and here we assume that A is an unbounded operator, let's say, which is defined in some suitable domain, which is subset of H, and it goes to H. Okay. And also we assume that A generates a semigroup ST. So if we are in ordinary differential equation case, like finite dimension case, then we can consider A as a simple matrix, let's say n cross n matrix, and the exponential matrix, exponential TA, will be the semigroup ST here. This is simple for ODE, okay? So here this control Q, we consider it is square integrable with respect to time, and as like this state, at time T, this Qt belongs to this control space, okay? And we assume that B is a bounded linear map from this control space to the state space. So B of Qt belongs to H. So everything in this equation is H valued, okay? So this is the usual setting for a control system. So as I mentioned that the main question is, let's say A and B are given to us. So we try to find the control in a suitable way such that this control can manipulate the trajectory of the system according to time and as we desire, right? So now under all these assumptions, we can prove that this system 1 has a unique solution, okay? So this is a very famous theorem by Haley and Yoshida. It says that this system has a solution under this assumption, okay? And by classical Duhamel's principle, we can write down explicitly the expression of the solution with the help of this semigroup and this operator B, right? So again, if A is a matrix, then we just replace this ST by the exponential matrix exponential TA, right? Okay, so this is the expression of the solution, which is the control system. Okay, now using this continuity of this semigroup and the continuity of this map B, we can prove the estimate of the solution like this. So at each time T, the norm of UT is less than equal to some constant, positive constant, times the norm of initial data and the norm of the control. So here we can say that our state at time T continuously depend on this initial data and the control, which is kind of source term. So here we don't need to put anything B here because B is a continuous operator. It can be, the norm of B can be adjusted inside this constant CT, okay? So this is a more or less well-posedness and continuity estimate for a control system. here I explain this for an abstract setting, but if we want to see some example and all these things, so the book Control and Nonlinearity by Jean-Michel Coran. In this book, actually, there are many examples for like heat equation, transport equation, Schrodinger or KdV. So all these equation has this existence theory in this book. This is a very nice, well-written book. Okay. So now we have a well-posed control system, which we will study the stability and stabilization for the system, right? So we start with system without control. So this is a free system, which is a ODE. Just take A is an N-cross-N matrix, let's say. For simplicity, you can take A is a 2x2 matrix. So U dot T equal to A of UT. So this is a differential equation. U is the state here, and U naught is the initial data, right? So we can easily solve this ordinary differential equation, right? This is the solution. UT is exponential T acting on this U naught, right? Now we'll see some definition. So what is called by stability? So stability means if for any epsilon greater than 0, we can find a delta which depends on this epsilon such that whenever our initial data belongs to a delta radius ball of Rn, then our solution should belongs to a epsilon radius ball of Rn for all t greater than 0. So if it happens, then we can say that the matrix A is stable, or rather the differential equation is stable. Okay. Simple example, let's say take a matrix 2 cross 2, 0, 1, minus 1, 0. Okay. We can easily find what is the eigenvalue of this matrix. The eigenvalue will be plus minus I, and we can solve this differential equation considering this matrix A. So this is just two components sin t and cos t is the solution of this differential equation with this matrix A. Okay. So now we see this sin t and cos t are bounded functions. So we always choose this delta according to epsilon. So in this case, actually, we can choose delta equal to exactly epsilon, and it works. So whenever this initial data, which is ordered table U01 and U02, it belongs to epsilon, we can prove that the solution for all time belongs to the epsilon radius ball of Rn. Okay. So this is example for stable differential equation. Okay. Another definition, which is called asymptotic stability, like we say that the equation 2 is asymptotically stable if the solution goes to 0 when t approaches to infinity. Okay. Another definition is exponentially stable. So this is the criteria we are interested in this talk. So exponentially stability means when we can prove that there exists some new positive such that norm of ut is less than equal to exponential minus nu t times the norm of u naught, and it should happen for all t greater than 0. If we can prove these things, we can say that our ODE is actually exponentially stable, right? So it is very easy to formulate such an example. Take a matrix A with diagonal element as a negative term, minus 1, minus 2. Then you solve this differential equation 2, putting this matrix there, and you can see easily that exponential minus t and exponential minus 2t as a solution of this differential equation, and it is very easy to check that this condition satisfied by this solution, right? And here one more thing is interesting, that exponential stability easily implies the asymptotic stability. It is very easy to check, right? And also for finite dimensional case, when we are talking about ODE, then this asymptotic stability also implies this exponential stability, and you can prove it easily by some contradiction argument. Okay. So yes, this is the three definition more or less we need to focus on. And as I said that these two things, exponential stability of the ODE and asymptotic stability, are equivalent. So we have one more implication with that, which suggested by this example, which says that if we can prove that the real part of the eigenvalue of the matrix A is all the eigenvalue are negative, that means the maximum of the real part of the eigenvalues of the matrix is negative, then we can prove that the system is asymptotic stable and this is exponential stable. These three conditions are if and only if condition for when we talk about ordinary differential equation. When A is a matrix, so these three are equivalent. So say to check that the equation is exponentially stable or asymptotic stable, we just need to check their eigenvalue. If the real part of all of the real part are negative, then we have this implication. Okay, but this is not true when A is an unbounded operator, like when we talk about PD. So these three conditions are not equivalent. Actually, asymptotic stability, exponential stability is the more strongest one. So it implies asymptotic stability and this negative eigenvalue condition, but the other two cannot imply this exponential stability for partial differential equation. So all these counter examples and all the implication for partial differential equation, you can check it in the book Mathematical Control Theory by Japjik. Again, it's a very nice book to understand all the cases for infinite dimensional system. Okay. Now we are done with the system without control. Now we'll go to system with control. So before going to that, this is a simple example. So he's trying to keep this broomstick in his hand, like stable. So he is watching in the top of the broomstick, and according to that observation, the brain sends the signal, and he puts place his hand in such a way such that he can make this stick stable. This is a very simple example of stability and instability, right? So the control is acting through his hand, and the observation is coming from the top through his eyes. Okay. So take the control system now. So u dot t equal to a of ut, b qt b is the control operator. Okay. First definition is that we want to study the control system through the help of the control, right? So when for any u naught belongs to H, there exists some positive number nu greater than 0 and a control q of u naught which belongs to this space square integrated with respect to time, and it belongs to q at each time t. So if we can prove that the solution of this control system satisfies this inequality, like is in its estimate, that norm of ut is less than equal to c times exponential minus nu t times u naught for all t greater than 0, then we say that the control system is exponentially stabilizable, right? Okay. So next definition which is important, this is called feedback stabilization. What does that mean? That if there exists a nu greater than 0 and a control with this special property, like control is depend on the state continuously, such that we need to find a bounded linear operator from H to Q, such that this control looks like Qt equal to K of ut, and if we put this control in the system and we can have this estimate, then we can say that our system is feedback stabilizable. Okay. So what is the difference between these two? Feedback stabilizability is one kind of exponential stabilization, but here our control has special form. So this control actually continuously depend on the state at each time t, right? Okay, so for practical scenario, this type of control is very important, right? So you can always estimate the cost of the control with the help of the state, right? So in this talk, we are going to focus on this feedback stabilization for heat equation and for other equation, right? This is the notion we are going to understand. So to prove that a system is feedback stabilizable, what we do? So let's say this is the control system, exactly same as the equation 4. So we need to find a continuous operator k from H to Q such that we need to put this control in this form q equal to k of ut. So let's say put this form qt equal to k of ut here. So b times k of ut, right? So you have this new system now. So what you need to check now after putting the control in the system? So you need to check this system is exponentially stable. Then automatically this definition holds. Like if you can prove that this system is exponentially stable, you can prove that this system is feedback stabilization, because this is the definition. Your control should have this form, right? For matrix case, like when we are in ODE, we will just check that whether this matrix is exponentially stable or not. If we can prove that this matrix is exponentially stable, then we can say that corresponding differential equation is feedback stabilizable. So this is more or less the definition, right? We need to do to find this matrix, or in PD, this is just an operator. Okay. So we consider again the control system in this form, like U dot T equal to AUT plus BQT. A is a n cross n matrix. Assume that B is a n cross n matrix. So here we consider n greater than equal to m. That means we have control, m number of control, and we have state, n number of state, right? So we try to control this system with less number of control. So that is very important in control theory, right? Okay. So now we have a criteria to check whether a system is feedback stabilizable or not. So it says that, let's say this rank of this matrix is n. So this is kind of a big matrix. So each entries you consider is as a n cross m matrix. So here B is a n cross m matrix. AB is again an n cross n matrix. An minus 1B again an n cross m matrix, right? So this big matrix is like it has n rows and nm number of column. So if we can say that this matrix has rank n, then we can prove that this system is feedback stabilizable. So this is a theorem. So here if we check, this is up to an minus 1. So why we do not need to go beyond n minus 1, because we know that a matrix always satisfies its characteristic equation. So you can always write a power n minus 1 with identity a square n minus 1 in this fashion, right? So we don't need to keep going after n minus 1. Okay, so now how we prove that this rank condition implies feedback stabilization, right? So a famous theorem by IM-UNAM from 1967, it says that if you choose any polynomial p with degree n, you always find a matrix K such that the characteristic polynomial of the matrix A plus BK is exactly that polynomial P. So what does that mean? So we want to prove that this system is feedback stabilizable, right? That means we try to find a matrix K in such a way this new matrix A plus BK is exponentially stable, right? So you see the characteristic polynomial of the matrix A plus BK is exactly P. So you need to choose only this polynomial P in such a way such that all its roots are negative, right? If all the roots of P is negative, then the characteristic polynomial of the matrix A plus BK are negative. So as soon as you get the characteristic polynomial of A plus BK matrix is negative, that means it has the eigenvalue of are negative, right? So since your eigenvalue of the matrix A plus BK are all negative, so the matrix A plus BK is exponentially stable, right? And this is the thing you want, to put this control Q equal to, let's say, K of U, and your system is now exponentially stabilizable. That means it is feedback stabilizable because your control Q is explicitly right, Q equal to K of U, right? This is, yes. It's okay. 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 So yes, this is you see the one way implication, right? This rank implies feedback stabilization. Okay. So you always construct a system which is feedback stabilizable, but it is not implies this rank condition. So this is one way implication, right? Yes, question.
Excuse my ignorance. Why do you need the extra dimensions on B?
Here?
Yes.
So the dimension means the number of state is greater than number of control. Like I don't need it because I mean if number of control is equal to number of state, it is very easy to control the system. But the important fact is that you need to control the control system with less number of control. So that's why this n greater than equal to m is important.
Thank you.
So again, now we have a if and only criteria here. It says that if the rank of this matrix A, comma B, so lambda I minus plus m column. So if the rank of this matrix is n, for all lambda belongs to C with non-negative real parts, you can prove that your system 5 is feedback stabilizable. Now we have a if and only characterization to check whether the system is feedback stabilizable or not. Okay. So this criteria is if and only, but the first one is not if and only. That is one way. Okay. So now this kind of characterization is exclusively hold for ODE. This does not hold for PDs actually. So in infinite dimensional case, we don't have such algebraic criteria. Okay. The important thing is that we need to find the control explicitly depends on the state. So that's why the backstepping method is important. So by previous theorem, we can check that whether the system is exponentially stabilizable or not. But the important thing is that your to state, right, explicitly. So before going to the method for heat equation, I just want to mention the method for simple ordinary differential equation. So let's say this is a control system, x1 dot equal to x2 and x2 dot equal to u, okay? So without this control, let's put u equal to 0 here. So you see x2 dot equal to 0, that means x2 is always constant, right? It does not change according to time. What does that mean? That means this system is not exponentially stable without control. So now we want to prove that putting the control in the system, whether we can check the system is feedback stabilizable or not, right? So what is the idea? Idea is somehow we need to transform this control system with another system which is exponentially stabilizable itself by some invertible transformation. So using that exponentially stabilizable of new system, we can prove the feedback stabilization of this control system. Okay. So let us take a transformation, a linear transformation from R2 to R2. So let's say y1 equal to x1 and y2 equal to x2 plus cx1. This is just a transformation, linear transformation from R2 to R2. Okay. Okay. Now we can easily check that this transformation is actually invertible transformation. We can always write x1, x2 with respect to y1 and y2. Like it's very easy to check x1 equal to y1 and x2 equal to y2 minus c y1 because y1 is x1. So this is an invertible transformation, right? Now easy computation shows us this y1, y2 satisfies this new set of ordinary differential equation. So what is that? y1 dot equal to minus cy1 plus y2 and y2 dot equal to minus cy2 y1. Now you see this y1, y2 satisfies this ODE provided we choose this control in such fashion. So this is just a simple back calculation, right? Now what is the importance of this new ordinary differential equation? You see minus cy1 and minus cy2 is very important to have the exponential stability of this new system, because if we check the eigenvalue of this matrix like minus c1 and minus 1 minus c, we can check that the of the eigenvalues are minus c. So it's very easy to check that this new system is actually exponentially stable, right? And in another way, we can prove the exponential stability. Just multiply this first equation with y1 and this second equation with y2, add them, then do integration. You can always prove this the stability estimate for this new ODE, right? And as I mentioned, this transformation is actually invertible. So you can always replace this y1, y2 and this initial data by x1, x2 and x1, 0 and x2, 0. Right? It's simple to check the invertibility of this transformation, right? So you replace this y1, y2 by x1, x2, and this is the things you are wanting. Just put a control u in the system such that you can prove the exponential stability of this control system without control which was not exponentially stable, right? So here see, u is the control. So this is continuously depend on the state x1 and x2, okay? So here, in this way, you prove the feedback stabilizability of this ODE through this control. This is the explicit expression of the control, right? Now a small observation with this transformation, y1 equal to x1, y2 equal to x2 plus cx1. So let's say we write this variable x equal to x1, x2 and y equal to y1, y2. So we write the transformation matrix minus some matrix k times acting on the vector x, right? Then this k will be in this form like 0, 0, 0 minus c. This is a lower triangular matrix, right? So this observation actually very important when we will go to the heat equation with this method. So you will see that this lower triangular matrix help us to generate some idea for heat equation, Okay, so this is the more or less method for ordinary differential equation. This is called backstepping method. And we are going to see this method for heat equation, which is one of the simplest PD, okay? So this is, now we move to the PD case. This is heat equation, ut equal to ux6 plus au. Here a is a real number, which is greater than 1. A can be space variable function, time dependent function, but here for simplicity, we consider A as just a real number, right? So the heat equation posed on this interval 0 infinity for time and open interval 0 pi for the space, right? We take 0 boundary condition, like at the two end it is 0 and u0 is the initial state, okay? Now if we write the corresponding operator for this heat equation, ut equal to ux6 plus au. Au is the operator, A of u is ux6 plus au, right? So its domain of A will be H2 intersection H1 0. So H2 for this Laplace operator, this is second order Sobolev space. And the notation 0 says that of the corresponding function, right? Okay. So we can easily find the spectrum of this operator. Just x6 u with this u0 equal to 0 and u pi equal to 0, right? So you have this eigenvalue minus k square plus a, and phi k sin kx is eigenvector, okay? Now, easily using separation of variable technique, we can write down the solution of this heat equation explicitly in this fashion, right? Series. So ak exponential minus k. What is ak? Ak is in corresponding to this initial data, right? And we know that sin kx forms an orthogonal basis for L2, okay? So we will use these things to check some stability criteria for this heat equation. So let's say first consider u0 as the first eigenmode of the Laplace operator. Just take u0 equal to sin x, right? So now check this ak here. So in spite of A, only A1 will be here, other than A1, all will vanish, right? Because you take u0 equal to sin x, you use the orthogonal property of sin kx, all the coefficient other than A1 vanish. So this summation just have this expression that A1 exponential A minus 1t sin x, okay? So other term of the summation vanishes, right? So now you see we take this A is greater than 1. That means we have a positive term in the exponential. So that means when t goes to infinity, so it blows up, right? So we have a exponential A minus 1t. So what does this suggest? That this heat equation with this A greater than 1 is actually not exponentially stable, or right? Or we can say that it is itself not stable. This is unstable, right? Cannot bound it in, with the boundness of this initial data. Okay, so now if we want to put a control in the system, everywhere in the system, now we can easily check that we can make this unstable system to a stable one, and it is very easy to do that. Right? So then is this plus A of u and this minus A of u out, you will only have minus lambda u in your new system, okay? So what change has happened, that the eigenvalue of this operator after putting the control will be minus k square minus lambda. You see all the eigenvalue are negative, and it's very good to talk about stability, right? Okay, so what is the new system after putting the control? T equal to uxx minus lambda u, right? And as usual we have this zero boundary condition, okay? Now we will check the exponential stability of this new system. It's very simple. We just multiply this equation with u and do some integration with respect to space from 0 to pi, right? After doing that, so first term will give us half ddt of 0 to pi u square, and here for the first term of the right hand side, we just do integration by parts, right? After multiplying u, this is minus 0 to pi u x square, and this term will be as it is minus lambda 0 to pi u square, right? So now we see this is a very good term as far as stability is concerned, right? This is a negative term. we can always ignore this term and we get this inequality, right? Half of ddt of integration 0 to pi square, 0 to pi u square is less than equal to this term. And you can use the ground wall inequality directly here, or introducing some integrating factors after integration. You can always prove that the L2 knob of the solution is less than equal to c times exponential minus lambda t u naught. Okay, so this is the things you are trying to prove that your system is exponentially stable with the help of this control with feedback form. So this is feedback stability. But actually the thing is that this whole criteria is very easy to do that, but it is not very interesting because you are putting control everywhere in the system. And this is just you are shifting the eigenvalue from right half of the complex plane to left half. Just that's it, right? So the important thing is that this question. So if we ask this question, right, you put the control in the boundary, like at the one end of the boundary, then can we do this exponential stabilization things or not? Because putting the control everywhere in the domain is not very good. At least in practical scenario, it is costly to put control everywhere. It is good to put the control in some smaller part of the domain. Here it is boundary, right? Here the backstepping method we are going to use. So this is a method many people actually work on this field, including Miroslav Krzyzczyk and Jean-Michel Coron and all their collaborators. So many equation has been studied for backstepping method. Let's say Burger's equation, KdV equation, KS equation, non-local heat, degenerate heat. Every equation more or less has been done with this backstepping method. And also we studied this method to particular equation. One is linearized compressible Navier-Stokes, and one is Firuk-Nagumo system, and we'll explain the result later. Okay. So in the book of Krzyzczyk and Andre, you can find a good explanation of this method for many simple PDEs. Okay. So now we are going to present a method. Normally, this is a theorem. It is called rapid feedback stabilization. That you choose a lambda as large as possible and fix it. Then for any u naught belongs to the space L2, you can always find a control with this feedback form k of ut, such that if we put this control in the system, you can prove the exponential stabilization of the control system with this decay rate minus lambda, whatever you chose earlier, right? So why it called rapid feedback stabilization? So rapid means you can choose this lambda as large as you want. So that's why it goes rapidly towards 0. So we mainly describe this method, and which taken from this paper by Liu in 2003. Okay. So this is the theorem we are going to present for heat equation. Okay. Take this control system and you consider again A is greater than 1, so that without the control, this is not stable or not exponentially stable, right? Now focus on this PD. So we already proved that this PD is exponentially stable minus lambda, right? By parts, you can prove that this new system with Z is exponential. Now the idea is somehow we need to convert this PD to this new PD with some invertible transformation, as we did for OD, right? So as we mentioned that this PD is exponentially stable. So the idea is to find a transformation which is invertible such that Z equal to KU or U equal to K inverse Z, so that we can convert this PD to this new PD, right? And with the help of this transformation and its inverse transformation, we can recover the exponential stability of the control system, right? So the main question is how we can convert this PD to this PD. What is the transformation in this setting, right? So we choose this Volterra integral transformation of second kind, which looks like ZTX equal to K of UTX, which is UTX minus integration 0 to x, kxy u to y. Here k is the kernel which satisfies some PD we need to find. We will explain what is the k. What is the advantage of taking this transformation? This Volterra integral transformation is actually invertible. And you see when we did it for ODE, we consider a matrix which is lower triangular. And here, this integration 0 to x gives us some idea, like this is kind of continuous generalization for lower triangular matrix to this 0 to x integration. We will see in the picture about the domain. So the one advantage of this transformation is that you can easily recover the expression of the control here by this transformation and the boundary condition. So what is that? Just put x equal to pi in this equality. So here you see zt pi equal to 0. So here this left hand side is 0, right? And you check right hand side, ut pi is exactly the control, and you put 0 to pi k pi y u ty dy. So that your control looks exactly these things, qt equal to 0 to pi k pi y u ty dy. So the control is explicitly depends on the state, right? So what does just happen? Like you have a PD, you know this new PD is exponentially stable. You want to find some transformation so that you can convert this PD to new PD. And with this transformation, you construct your control easily with the help of these two boundary condition, right? Now only thing we need to check, what is the kernel kxy here, okay? So easy computation shows that you can check this PD convert to this new set of PD if this kernel satisfies this wave equation, which is kxxy minus kyyyxy minus lambda minus a kxy equal to 0. And we have two boundary condition, which is in the base of this triangle and this along through this diagonal. Now we see this boundary condition is little bit unconventional when we talk about wave equation for Cauchy problem. We used to give the boundary condition along the edge, but here we have the boundary condition of this triangle along these two lines, the base and diagonal. Okay, so here the lower triangular kind of matrix says to have this idea to take the Volterra integral transformation from 0 to x. Okay, so now question is how we can prove the well-posedness of this kernel, like how we can prove this kernel equation has a solution. Okay, so we know that this wave equation has the characteristic of the form x plus y and x minus y, like this V shape, right? So we take this change of variable j equal to x plus and eta equal to x minus y, and we take a new function g of xy, right? Find what is the equation satisfied by this new function g. So this is the equation, we can compute that equation of g by the equation of k with this change of variable. So this equation of g is much more simpler than the equation of k. So it has two partial derivative with respect to j and eta, and it has two condition also. So what we need to do to prove that this equation has a solution, we will use some kind of integral equation theory, right? So we integrate it with respect to eta first, and then we integrate it with respect to j, and we will use this boundary condition, and we get this integral equation. Now we need to prove that this integral equation has a solution. So if we can prove that this equation has a solution g, then we can say that this equation has a solution g, and in this way we get the explicit expression of the k and the existence of the k. And as soon as we get the existence of k, so we complete the backstepping method, right? So now how we can prove this this integral equation as a solution? So this is very easy. We all do for ODE courses, like we know the Picard iteration, right? How to solve these things. Just take a map T from some space to space X, so that T of G equal to what you want to prove, that this map T has a fixed point. If this map T has a fixed point, then we are done, right? Because T of G equal to G and G equal to this term. This is the exactly. So the fixed point will give us the solution of the differential equation. So to prove that this map has a fixed point, we just use some iterative scheme. Consider first G0 like this term, and consider a sequence Gn equal to this second term with replacing G by Gn minus 1. Then try to find that this Gn is a Cauchy sequence and it has a convergence subsequence. and the limit of the convergence subsequence will give you the fixed point of this map, and the fixed point is actually this G. So in this way, you can get the solution of this PD and the solution of this kernel, right? So you can complete the method, okay? So before finishing the method, I just want to explain it one more time. So what just happened? Let's say we have an unstable PD and we know that this system is exponentially stable. We try to find some transformation so that we can convert this PD to this PD and vice versa, right? And with this conversion, we can prove that exponential stability of this unstable heat equation with the help of the control, which is explicitly written here, and it is in the feedback form, right? Because your control is continuously depend on the state here. And this is the kernel equation. We just proved that this equation has a solution, okay? Now, this backstepping method also has some limitation. So first consider these two heat equation, ut minus uxx equal to v, and vt minus vxx equal to u, right? So this is a coupled heat equation with zero order coupling, and you put two control in the boundary. So adapting the previous method, here you can easily prove the feedback stabilization of this coupled system with the help of these two control, right? You need to take two different transformation, and just mimicking the same argument, you can able to prove the feedback stabilization of this equation. Now, the question is, if we stop one control, we can prove this method for this equation, but no, this is not the answer. So we don't know that how to do this thing with one control. In control theory, it is very important. It is always important. But in the controllability perspective, this equation is well viewed when we ask the question that this equation is controllable with one control or not. We know that moment method, there is a method, moment method, which is very good to use to have this controllability of this system with one control. But for backstepping with stabilizer, no, we don't know how to do it. There are some problem with the kernel equation. So next question is, can we do these things with when control acting in the interior of the domain? Let's say take any smaller interval AB in the domain, put the control here. Can we explore the backstepping for this setting? No, this answer also no, we don't know. This is not proof that we cannot do, but so far we don't know how to do it, okay? And again, whenever we do something for one dimension, the very basic question is, can we do it in higher dimension? Okay, so if we take any circle, polar coordinate thing, or we take square domain, we can do Fourier expansion, everything boils down in one dimension setting. In that case, we can do, but for general geometry, this method we don't know that how can be applicable for this kind of particular domain, okay? So despite of this drawback, we have some good news for coupled system with backstepping. So this is the compressible Navier-Stokes equation. We try to find the feedback stabilization for this equation, but we are kind of nowhere near to attack this whole nonlinear problem. So whenever we encounter any difficulty with nonlinear problem, what we do, we linearize it around some steady states, sometimes trajectory or something, just to simplify the equation, okay? So again, here so we linearize this nonlinear system with this steady state Q naught 0, and we get, let's say, this equation. So first equation is of density, second equation for velocity. So this is the equation. The second equation is kind of heat equation with this coupling. This is just an ODE, right? No space variable involved for density. This Ux we can consider as a source term. Let's say take this Dirichlet boundary condition, and this is a coupled ODE parabolic system as I described. So now we want to show that exponential stability of this compressible Navier-Stokes system. Okay. First, let us write down the system with this abstract form. U dot equal to A of U. U is the state, rho and U, and rho naught, U naught. is the initial data. So A is the corresponding operator. So if we try to to see what is the spectrum of this operator A under Dirichlet boundary condition, we can see that this is the spectral behavior of this operator. So it has two branches of eigenvalue. One goes to -infinity, which is good when we study feedback stabilization because we want everything in the left half plane. But here we have a set of eigenvalue which is fixed, like it converges to some fixed point. So this fixed accumulation point of the eigenvalue actually describe the exponential stability result for this Navier-Stokes equation, because we cannot talk about rapid feedback stabilization for this particular case, because this accumulating branch actually creates some problem to go beyond the decay rate of this point. Okay, we will see the result. Before I explain what is the result, this is the spaces we are going to consider. First, H1 space is the Sobolev space first order, like f is in L2 and the weak derivative in L2. So H10 is, it is in H1 but with the boundary condition are 0. H1 curly 0 is that it is H1 but it is 0 only at the point 0. And H1m is, it belongs to H1 but the mean value of this function, like integration from 0 to pi, is 0. Okay. So these three spaces has a similarity, like the point Poincare inequality holds for these three spaces. Okay, and actually helps to get some estimate. So there are some known results regarding linearized Navier-Stokes for stabilization. It says that if you take this initial data in these spaces, then the system is feedback stabilizable with a decay rate when omega naught is explicitly the accumulating point of the spectrum, right? This is one known result. And this result says that this system is not stabilizable with a decay rate omega when omega is greater than omega naught. That means we don't have any exponential stability with exponential minus omega t rate when omega is greater than omega naught. So these two papers actually use spectral analysis of the corresponding operator of the Navier-Stokes equation and the explicit expression of the solution of the equation. So since the spectrum has this accumulating branch, so we cannot speak anything what happened when omega equal to omega naught. But you see in backstepping method, we did not use anything regarding spectrum. It is, we are using the equation. So that's why this backstepping method is very much useful to talk about that what happened when omega equal to omega naught. Like can we go to the decay rate up to exponential minus omega naught t decay rate. So in this method actually we not only consider Dirichlet boundary condition, we consider the Neumann boundary condition and mixed type boundary condition. So our result, we will take any of these three boundary conditions, we consider backstepping method and we prove the exponential stabilization result up to the decay rate exponential minus omega naught t with the, okay, so this is a result we proved that take any omega belongs to this set. You see here is a closed interval, like we can touch the BQ naught, nu naught point here. With this help of this backstepping control, we can prove that feedback stabilization of the system with the decay rate exponential minus omega t. So this omega, like the end point can be achieved here, right? This is the result for linear ODE parabolic system. So now I just end this talk by explaining this result for a nonlinear ODE parabolic system, which is called Fiduk-Nagumo type system. So this first equation here is heat equation with some nonlinear term, right? And second equation again an ODE. So we put boundary condition ut0 equal to 0 and ut1 equal to q1t. This is the initial data. Okay. So we call the system is Fiduk-Nagumo system if it has this U cube type nonlinearity. This is a linear term because rho is just a positive constant. And the system is called Roger-Maculo system if it has two type of nonlinearity, like first one is U cube type nonlinearity and second one product nonlinearity. So we have the product of two states here, right? So according to the nonlinearity, this system has two properties, like first one is Fiduk-Nagumo, second one Roger Macula. So we want to study the backstepping method for this system, because we see that this nonlinearity is not much stronger than Navier-Stokes nonlinearity, because it is little bit easy to use the backstepping method. So we exactly use this method for this system. So as usual, we write the equation with this abstract form, u dot t equal to AUT, just to find some properties of the operator. So first one is the operator for Roger-Macula system. This is for FHN. These two operators are just according to the nonlinearity. So again, like Navier-Stokes case, we have a accommodating spectrum branch. So that's why we cannot prove the exponential stabilization beyond some point like delta. Our exponential stabilization is up to the point delta. Okay. So before going to the feedback stabilization result, this is called local feedback stabilization. What does that mean? Exactly same definition, just you need to find some positive number r such that your initial data belongs to a small ball of a radius ball of L2 cross L2, right? So this is the local feedback stabilization. You need to find some control Q in this form such that it depends continuously with respect to state. So whenever your initial data belongs to this small ball, you get your stabilization result. So this is why this is called local feedback stabilization. So your initial data is not arbitrary. Okay, so there are some results regarding backstepping method with nonlinear model. First one is for Fisher equation, and second one for KDP equation. Actually, these two papers helps us to understand the method for nonlinear model. Okay, so these two papers are well-written paper to understand the method. Next, this is our result. We take the decay rate omega belongs to this set. Delta is the accommodating point. So we have a positive number r such that whenever our initial data belongs to this set, we can find a control, backstepping control, such that this exponential stabilization result holds. So this is the feedback stabilization result for these two systems. I just wrote it in the same slide. Okay, so now question is, what is the difference between linear backstepping and nonlinear backstepping? The difference is not much, it kind of same. You need to take these two new variable u tilde and w tilde with the help of this operator k as we define it for the heat equation. And you check that your new variable u tilde and w tilde satisfies this equation. Now see, if you have a heat equation only, you get this u tilde t minus u tilde xx equal to minus lambda u tilde, and you don't have any nonlinear term. But here, since we are working with nonlinear equation, we get some difficult nonlinear term here. So what we need to do? We need to estimate this nonlinear term one by one, and at last we will use some local Williamson's result to finally conclude the exponential stabilization result for this nonlinear system. So only difficulty of this case is just to use the energy estimate for this nonlinear term. So what we will do? We will do some apply some Young's inequality repeatedly and use some basic Sobolev embedding theorem to cancel out some bad term. Okay, so this is the explicit control of the system we are using. So yes, this is the thing, and I want to stop here. Thank you, everyone.
¿Hay preguntas para Subrata? I do have one question while other people think of questions. When you were first explaining the backstepping method, there was a step where you made a change of variables going from the Volterra kernel to some other function g.
Yes.
I think I missed the point of that. It seemed like the change of variables was just a rotation, and it didn't seem to like change the shape of the domain or anything, so I didn't see what the advantage was.
For taking this...
Yes, at some point, I think it's a little bit earlier in the slides, you went from that function k to a function g, and the change of variables was something like
I understand
eta is x, that one. Sorry, it
Maybe
flashed
here.
by on the screen. You had like, I think it's the next slide.
Or the,
No, in the other direction.
okay,
Yes.
I think this one.
Wait, so there was at some point you had like, I think it was eta is x plus y and nu is x minus y, and you wrote the,
Oh, okay, I understand. Yeah, I understand the point.
and
Yes.
I didn't understand what that transformation made easier. No, sorry. It's, I think it's a head. It's there, right there.
Here?
Yes.
Here? Okay, yeah.
I didn't understand what this transformation made easier, that variable change.
This change of,
Yeah.
this change of variable?
Yes.
Okay, so let's say we want to solve this differential equation, right? So we know the wave equation has the characteristic kind of this, right? Like maybe other way. This kind of characteristic it has, right?
Yeah.
So what we try to convert this system to a simpler system. Okay.
Yes.
So we use the change of variable along this characteristic. Let's say just take any function g I eta equal to kxy. For the timing, we don't know what is g. So we will first we take the derivative of g with respect to j, eta, and all those. We put all the variable for this g, and by seeing this equation for k, we able to combine everything, and we can find the equation of g.
Sorry. So it's that first equation that got simpler.
Exactly.
Yeah.
The first.
Okay. Sorry. That
first
I had just missed.
I
That.
mean, you
Thank you.
you just need to find, let's say, what is gi first.
Yeah.
What is
Yeah.
g eta. In this way, you arrange all the derivative and check like what is happening with this k, and putting together, you can able to manage this differential equation. Yes, just to make simplify, because you see the equation of g is kind of simple.
Yes.
rather
Yes.
than
Thank
k.
you. Sorry.
Yeah.
¿Hay alguna otra pregunta? ¿No? Bueno, sí. Actually, did have another question now that I remember. When you showed us the coupled parabolic equations, and yes, here when you discussed that you can control this case, but that you can't with a single control.
Yes.
The definition of a single control was, I think it was not what I expected. I thought the single control case would just mean that Q1 and Q2 had to be equal. But instead, I think you had just Q2 equal to 0.
Yes, because that question is more difficult to have the stability with same control.
Yeah.
Is the important first thing is that just to prove it with one control, and your second, this question is come second, like can you control the system with same control in
with
the
same
question?
control.
Yes.
And so that's easier than the 0.
No, that's difficult.
Okay.
That's difficult. At least from control theory point of view, this is easy little bit.
Yeah.
But that question is more difficult. But we don't know the answer of this question.
Okay. I see. Yeah. Okay. Thanks.
Coupling with
Okay.
instead of it's like similar to that. So you want less controls than equation. Even if you have two fit equations.
Right.
So the other problem you are saying
Yeah.
has other issues.
So
So if you want to put the same this one in but in other cases it's another.
¿Hay alguna otra pregunta? Si no hay más preguntas, démosle las gracias a Subrata de nuevo.